Hi, good afternoon. My name is Tang Le. I would like to welcome you to the 2021 AMS Maryam Mirzakhani Lecture. This lecture, inaugurated last year, is to honor and commemorate the great mathematician Maryam Mirzakhani, the first woman Fields medalist. Mirzakhani was a professor at Stanford University who made fundamental contributions to hyperbolic geometry, complex analysis, topology, and dynamics. It is my great pleasure to introduce the speaker of this year's Maryam Mirzakhani Lecture, Professor Ciprian Manolescu, also from Stanford University. Professor Manolescu works in the field of low-dimensional topology and gauge theory. Among many of his achievements is a spectacular disproof of the triangulation conjecture for manifolds in dimension 5 and higher. Professor Manolescu has received numerous awards and prizes, among them the prize of the European Mathematical Society, the Moore Prize from the American Mathematical Society, and the Simons Investigator Award. Both Manolescu and Mirzakhani were winners with perfect score at the International Mathematical Olympiad for high school students in 1995. And both went on to get their PhD at Harvard in the same year, 2004, and then both work at Stanford. And today we have Professor Manolescu as the speaker of the Mirzakhani Lecture. He's speaking on Khovanov homology and surfacings in four manifolds. The talk is 50 minutes long. Then we have about 10 minutes for questions and answers. If you have any questions for the speaker, please post them in the Q&A box, and the speaker will answer them after the presentation. Now, please join me and welcome Professor Manolescu.
Thank you, Tang, for the introduction. Indeed, I knew Maryam from when we were both graduate students, and it is a great honor to give this lecture in her memory. I wanted to thank the AMS for inviting me to speak, and I want to thank you all for coming to my lecture, especially since I know that our political situation and the events in Washington yesterday are on many people's minds. But yes, thanks for coming to listen to some mathematics. All right, today I will be talking about Khovanov homology and surfaces in four manifolds. Here is an outline of my talk. I will start with a review of four-dimensional topology, some major results. Then I will be talking about Khovanov homology and its applications. And then at the end, I will discuss a strategy to construct an exotic force sphere. This is not yet a successful strategy, but there's been some progress, and I will tell you some recent results. Okay, so 4 dimensions, topologists know that they are very special. In low dimensions, up to 3, you can understand manifolds. You can definitely classify surfaces by genus, and then you can understand manifolds of dimension 3 using geometric methods like hyperbolic geometry. And this was the basis of the Thurston geometrization program, and for example, the proof of the Poincare conjecture by Perelman. Now, in dimensions at least 5, there is also some work that was done in the 60s, which led to the classification of at least simply connected smooth manifolds based on surgery techniques. So much is understood. The analog of the Poincare conjecture is known. And the basic reason why dimensions at least 5 are in a sense easier is because there is enough room to keep disks apart from each other, or two-dimensional objects. Because 2 plus 2 is less than 5, if you have 2 disks that intersect, you can move one a little bit and there will be disjoint. And that's at the heart of the proof of the H-cobordism theorem, which leads to this classification. But dimension 4 is more difficult, and it's one issue is that it's the first dimension where we need to make the distinction between topological and smooth manifolds. This distinction also appears in higher dimensions. Topological manifolds have been understood to a large extent since the work of Friedman in 1982. But smooth manifolds are still a mystery. Okay, so when I talk about, I'm going to talk a lot about exotic smooth structures. An exotic smooth structure is given by a manifold that's homeomorphic but not diffeomorphic to X. In general, a smooth structure on X consists of manifolds homeomorphic to X modulo diffeomorphism. So a famous example is, you can just think about Rn, and that's where you see that n equals 4 is special. Rn has a unique smooth structure for n different than 4, but in dimension 4, it has uncountably many. You can also think about the sphere, the n-dimensional sphere, and there the smooth structures are unique in many low dimensions, like 1, 2, 3, 5, 6. They stop being unique for like in dimension 7, but then there is a way of understanding how many there are in terms of the stable homotopy groups of spheres. So it's an algebraic topologic problem. But in dimension 4, this is completely unknown, and this is the smooth Poincare conjecture, which is still open. And it asks, if a smooth 4 manifold is homotopy equivalent to S4, then is it diffeomorphic to S4? And by the work of Friedman, we know that it is at least homeomorphic to S4. So if such a manifold exists, it would be an exotic smooth structure on S4. And unlike many other conjectures in mathematics, experts disagree or don't have an opinion in many cases on whether we should expect this to be true. We really don't know. It might be true or it might be false. What I'll talk about is some strategies that aim to disprove it. This is based on the fact that many potential counterexamples exist and have been proposed over time. So these are manifolds that are homeomorphic to S4, but are not known to be diffeomorphic. Now, typically, in many cases, they were first proposed as counterexample, but then other mathematicians show that they are the same as S4. But later, other people made new counterexamples, and there's always a supply, but then there's also proof that they are standard. So this led some people to believe that maybe the conjecture is true. Still, we don't really have much idea about how one could prove it. So instead, we do have some ideas about how we could possibly disprove it. So I will talk about that later. All right, now in 4 dimensions, the one technique that produced a lot of results was gauge theory. So this was introduced by the work of Donaldson in 1982 and consists in using partial differential equations, typically coming from physics, like the Yang-Mills and the Seiberg-Witten equations, which have a gauge symmetry. Gauge symmetry refers to having a symmetry under the infinite dimensional group of automorphism of a bundle. So it's a differential equation involving connections and section of a bundle, and it should be invariant under this gauge group. So let me just review some major results that were proved using this method. So the first famous one was the Donaldson diagonalizability theorem, which says that if you have a closed, simply connected, smooth four-manifold, and its intersection form on the second homology, so you can think of it as surfaces intersecting in the four-manifold. If this is either positive definite or negative definite, then this bilinear form can be diagonalized over the integers. So over the complex numbers, you can diagonalize anything, but over the integers, it's not quite the case. So for example, there's the E8 form. And in fact, Friedman showed that there exists a topological four-manifold with the E8 intersection form. And by this Donaldson theorem, it follows that it cannot be smooth. So there exist non-smoothable four-manifolds. And also another corollary of this theorem with some more work, you can deduce from it that there exists these exotic smooth structures on R4. Now, what are some other applications of gauge theory? For closed manifolds, what you do is you count the solutions to these PDEs and you get invariants of the manifolds that depend on the smooth structure. So they're not like homology or homotopy groups, which just depend on the homotopy type. They actually depend on the smooth structures so they can distinguish exotic ones. And using them, you can find exotic smooth structures on many closed four-manifolds. So, for example, the K3 surface or CP2 plus n capitals of CP2 bar, where n is at least 2. Here by CP2, I mean the complex projective space. I gave the definition. And CP2 bar is the same complex projective space, but with the opposite orientation. And plus denotes connected sum. So basically connecting two manifolds by a tube. So CP2 plus n CP2 bar corresponds in algebraic geometry to blowing up CP2 n times. Yeah, so these are known to have exotic smooth structures, but what we don't know is about small closed four-manifolds, like if you only blow up once or 0 times, so on CP2 itself, or S2 times S2, or of course S4, where we have the smooth Poincare conjecture that's still open. So typically, the bigger, the more complicated the four-manifold, the more chance you have to find an exotic structure. One other thing that four-dimensional topologists are interested in are surfaces inside the four-manifold. So a basic question is, if you are given a homology class, it's a classical result that you can represent it by a surface, and you can ask, what is the minimal genus of that surface? And for example, using gauge theory, Kronheimer and Brovka answered this in CP2. They showed that in the homology class D of degree D, so D times CP1 in CP2, the minimal genus is D minus 1 times D minus 2 over 2. This is what's given by a smooth algebraic curve in that class. The result was extended later by Oshvat and Szabo, who proved that in general, symplectic surfaces in symplectic manifolds, in four manifolds, are genus minimizing in their homology class. So in particular, complex projective surfaces are symplectic, and complex curves in them minimize the genus. And their proof is based on something called the adjunction inequality, which gives you a bound on the genus of surface in a four manifold in a given homology class in terms of the Seiberg-Witten invariance. There is also a relative version of this question. So instead of a minimal genus of a closed surface, you can ask about the minimal genus of an open surface, namely, or a surface with boundary. And you can ask this even in the four ball. So you fix, so B4 has boundary S3, and you can look at a knot in S3, so a one-dimensional connected submanifold. And you fix the knot in the boundary, and you look at what's the minimal genus of a surface with the boundary, that knot, so four-dimensional. In the four-dimensional ball. That's called the slice genus. And there exist non-trivial genus that have even slice genus 0, and those are called slice. So this bound something of genus 0, namely a disk. So they bound a disk in 4 dimensions. Here is an example of what such a disk can look like. This is a knot called the square knot, and the disk is the colored one. It has self-intersections, but you can think of in 3 dimensions, but the colors should correspond to the 4th dimension if you want. So when they intersect in this way, you can think of it as moving in the 4th dimension. So it's an embedded, it's a smoothly embedded, I'm talking about smoothly embedded surfaces. So in 4 dimensions, it's embedded. So many small knots are not sliced, but some of them are. I should mention there's also a weaker notion. So here in the above, we talked about smooth surfaces, but you can ask about topological surfaces. And you want a technical condition that they come with colored neighborhoods. So they look locally like smooth surfaces in a sense, but topological, but just topologically like that. And yeah, and then you can ask about which knots bound such topological disks, and those are called topologically sliced. And that's a weaker condition. So some knots are topologically sliced. Now, what's interesting is that one open problem in knot theory is that to find the slice genus, given a knot, what is the minimal such genus? And there is no known general algorithm for doing that. Not even a very inefficient algorithm, just no algorithm at all. We are not able to tell when a given knot is sliced. However, in some cases, for some knots, we can compute a slice genus, and that's another application of gauge theory. So a famous result is the Milnor conjecture, which was proved by Kronheimer and Mrvka, which says that the slice genus of the torus knot is given by p minus 1 q minus 1 over 2, where the torus knot is something like in the picture here, where you look at the standard picture of the torus in space, and you wrap p strands q times around the meridian of the torus. So for example, this is T3 minus 8. So for this kind of an infinite family of knots, gauge theory allows us to compute the slice genus, the minimal genus of a surface with boundary in that knot. Okay, so this was a quick review of 4 dimensions. Now let me talk about Khovanov homology. Khovanov homology is some tool that's not about gauge theory, but it has similar applications. So this was defined in 1999. It's an invariant of knots or of links in 3-dimensional space, and it's a 2-dimensional. It's a bigraded abelian group or bigraded vector space if you want to work over a field. And the definition is quite elementary. I can basically give it to you in a couple minutes. What you do is you look at the diagram of the knot. Like in this case, I'm looking at a link with 2 components in the picture below, and I'm taking all possible resolutions. So at every crossing, I even resolve the 2 strands. I drew it like this or like this, and this way I get a bunch of circles instead of a link. And I put all these possibilities into some hypercube. In this case, it's a square. And now to every circle, I associate a given 2-dimensional vector space V. And then I'm defining some differential. I'm making a chain complex out of the direct sum of all these. And D is just algebraically defined. The differential is, well, if you notice in this cube, you have either circles getting joined together or a circle being broken up into 2 pieces. And there are just some formulas for these, some algebraic formulas. So V is a 2-dimensional vector space. Let's say the generators are 1 and x. Then you define some multiplication and some co-multiplication by these formulas. And you use this to define the differential on the complex. You can prove that d squared equals 0, and the homology, when you take homology, you get what's called Khovanov homology nowadays, and that's not invariant. Okay, now, so Khovanov homology was constructed combinatorially, and it's of interest to nowadays. It has connections to many branches of mathematics, in particular to representation theory. It's closely connected to the categorification program. Its Euler characteristic is another famous not invariant, the Jones polynomial. By Euler characteristic, I mean, well, usually when you have a homology theory, it has a degree, and you take the alternating sum of the dimensions. In this case, it has 2 degrees, I and j. By the way, I didn't tell you the definition of the degrees, but all these vector spaces that I mentioned before, they are bigraded, and and you get a bigrading on the homology, and you keep, when you take the Euler characteristic, you keep track of one of the gradings by a power of q, and you get some polynomial by taking the alternating sum with respect to I. And what makes Khovanov homology interesting from the point of view of 4 dimensions is that it is functorial with respect to surfaces in 4 dimensions. Namely, if you look at a cylinder like S3 times 0, 1, I drew a picture here of a surface in this cylinder. On one side, you have a knot, and on the other side, you have another knot or link. They can be links. If you have a surface, you get a map on Khovanov homology from that of K0 to that of K1. And this is a functorial assignment, so they compose nicely. So this tells you that this has something to do with 4 dimensions, except it's just about surfaces embedded in some very simple 4-dimensional manifold. Okay, so Right, so what's interesting is that Khovanov homology can be used as a replacement to some extent for gauge theory, and the first indication of that was the Rasmussen invariant. So using a deformation of Khovanov homology in 2004, Rasmussen extracted from it some number, some numerical invariant of knots, which he called S. And he proved, using this functoriality property, using the fact that it behaves nicely with respect to surfaces, it proved that S is a lower bound for the slice genus. So remember, the slice genus is the minimal genus of surfaces in 4 dimensions with boundary the knot, and it's hard to compute. It's hard to give lower bounds for it. It's easier to give upper bounds in a sense because you just exhibit a surface. But for lower bounds, the S invariant gives you a method of giving one. So that's what he proved. And as a corollary, he gave a combinatorial proof of Milner's conjecture, the one that I mentioned that was first proved by Khovanov and Mruvka about the slice genus of torus knots. And from here, another application is that you can show the existence of topologically sliced knots that are not smoothly sliced. I mean, basically, you can find some knots that are topologically sliced, but S is non-zero. So S is about smooth surfaces, I should say. It was known before, like after some topological constructions from this kind of knots, topologically but not smoothly sliced, you can get exotic smooth structures on R4. So this was a proof using like more elementary methods without gauge theory. Even some more recently, even other results. So Rasmussen's results were mostly about, were about B4, which is a simple four-manifold. But you can also get results about CP2. So the Thom conjecture, about which was proved by, again, using gauge theory about the minimal genus in CP2, was reproved by Lambert-Cole in 2018 using, again, Rasmussen's invariant, plus some contact geometry and this new way of visualizing four manifolds in terms of trisections, which is due to Gay and Kirby. And that allows to split CP2 into 3 parts, and each of them are easier to understand. They're pretty simple. So you kind of reduce it to the case of B4 or some other simpler four manifolds. And even more recently, Peter Lambert-Cole extended these methods and he proved the adjunction inequality in general symplectic four manifolds, so much more general than CP2. And from here, he deduced the symplectic Thom conjecture. And also, he gave a proof of the existence of exotic smooth structures on some closed four manifolds, like K3 blown up ones, for example. So it's quite interesting that just starting from a knot invariant, which has something to do with surfaces in B4, you can look at very complicated four manifolds, but split them into relatively simple pieces. And if you put all these ingredients together, you can reprove very deep results that were originally proved using gauge theory. Still, I mean, not everything is done. So not all the gauge theoretic results have proofs based on Khovanov homology. For example, Donaldson's diagonalizability theorem is still, has still not seeded, still does not have such a proof. Okay, so these were just new proofs of old results. Now, what about some new applications? Can Khovanov homology do anything new that gauge theory couldn't? And here is one cool application having to do with this knot, which is called Conway's knots. And what's interesting about it is that, well, it's topologically sliced. It has S equals 0, so you cannot tell based on S if it's sliced or not. And in fact, many other obstructions that people know to sliceness vanish. So this made it sound that maybe it's sliced, but we couldn't find a sliced disk. And in fact, up until 2 years ago, it was the only knot up to 12 crossings. It has 11 crossings, by the way, that was not, whose sliceness status was not known. So for all the other knots up to 12 crossings, it was known whether they are sliced or not, but not for this one. So in 2018, Piccirillo proved that this is in fact not slice, and I want to sketch a little bit of her proof because I will need some notions from it, and it's quite interesting. So her proof starts by considering this knot trace. The knot trace is a four-dimensional manifold that you can build out of every knot. The way you do it is you start with a four ball, and the knot is on the boundary, it's in S3, and then you attach what's called a two handle. A two handle is just a neighborhood of a disk. So you attach a disk, and then you attach, instead of a disk, you attach D2 times D2, a four-dimensional thing. And together with the original ball, you get a four manifold with boundary. That's called the trace. And the boundary also has a name. It's called the zero surgery on the knot. So the boundary is a three manifold. And you can think of it as in a different way as obtained by surgery. Basically, from S3, you take out a neighborhood of the knot. A neighborhood of a knot is a solid torus. I mean, yeah, the knot is just a curve. It's embedded in a complicated way, but a neighborhood in R3 is a torus, is a solid torus. And then you put back, so you take it out and you put it back, but by an interesting gluing. You want the gluing to reverse the meridian and the longitude of the boundary torus. So if you do that, you get a three manifold called the zero surgery, and that's the boundary of this four manifold. Okay, so one lemma is that you can characterize the sliceness of knots in terms of the trace, whether it embeds in B4. So this is a relatively simple known lemma. I don't have time to prove it. But based on this, this is how Piccirillo's proof goes. You show that the Conway's knot is not sliced by constructing a partner knot, C prime, that has the same trace. So the traces are diffeomorphic. And therefore, by the trace embedding lemma, if one embeds in before, then the other does. So C being sliced is equivalent to C prime being sliced. But then she fed C prime into, C prime is a much more complicated knot. She fed it into a computer, and it got that S is non-zero. So S is non-zero. It means that C prime is not sliced, and therefore C is not sliced. Oh, I should mention, so S, remember, S is the lower bound for the slice genus. So if the slice means that the slice genus is zero, that the knot bounds a disk. So if something is sliced, then it needs to have S equals 0. Okay, so this was the proof that Conway's knot is not sliced, and there's no known proof using gauge theory. So sometimes Khovanov homology can go beyond what was known before. Now, this was something about knots. Now, what about four manifolds? So we saw that with Khovanov homology, you can reprove some old results. Now, how about some new results? Well, that's nothing. Okay, nothing concrete yet. But what the hope is, well, one hope is to use Khovanov homology to construct new invariants, just like the Seiberg-Witten or Donaldson, but maybe this would give some new invariants of four manifolds. And there is some recent proposal of Morrison, Walker, and Wedridge called the Skane-Lasagna algebra. So they have some four-manifold invariant based on Khovanov homology, but it's hard to compute. So far, it's just been computed for some simple four manifolds. I wrote a paper with Natalat, where we computed it for CP2 and some disk bundles over S2. So I won't mention this too much. Instead, I will discuss some hope about a possible approach to the smooth Poincare conjecture in dimension 4 based on Khovanov homology. This is an old idea. Okay, so what would be the strategy? The strategy, I wrote it here in blue. It first appeared in a paper by Friedman, Gumpf, Morrison, and Walker. And it's based on using Rasmussen's S invariant from Khovanov homology as follows. You find a knot in 3 dimensions that's not sliced because S is non-zero, but it doesn't bound a disk in B4, but it bounds a disk in a homotopy ball, in a homotopy B4. And that would show that that homotopy ball is not B4. And from there, you can deduce that if you add B4 to it, you get a non-trivial homotopy 4 sphere. So, I mean, you could try to do this with other invariants, but in gauge theory, the way it works is gauge theory cannot really distinguish between sliceness in B4 or in a homotopy B4. But for Khovanov homology, we don't know. So yeah, it's just not known whether S can help, whether there exists such a knot. All right, so to attempt this strategy, you will need some good source of examples of homotopy 4 balls and also knots that bound disks in them. All right, so this strategy is still open, but well, I mean, it's open whether it works, but I will describe 3 recent results about it. So the first, so let me first start with one way of constructing potential counterexamples, which is called Gluck twist. So Gluck twist, the Gluck twist starts with a 2 knot, which is an embedded sphere in S4. Then what you do is you take out a neighborhood, N, which is diffeomorphic to S2 times S2, and then you put it back. So it's some sort of surgery. And again, you put it back by a non-trivial diffeomorphism, namely this one, where you rotate by the angle on S1, you rotate S2 by a rotation with a fixed axis and depending on the S1 factor. And you can show that if you do that, you get a homotopy 4 sphere. And well, there are many constructions of 2 knots, just like there are many constructions of knots in R3. There are many constructions of 2 knots in S4. And for many families, you can show that what you get is S4. But it's not known whether this is true in general or not. Okay, so here is one result, which is more of a negative result, which is based on work of, so it's work of that I did with Marengon, Sharkar, and Willis, which says that the strategy that I mentioned fails for Gluck twist. So that's because if K bounds a smooth disk in a homotopy 4 ball obtained by a Gluck twist, then S is 0. So S cannot detect between knots that bound disks in such a Gluck twist versus slice knots, those that bounded in B4. So here is the sketch of the proof. We show that well, this has something to do about surfaces in CP2. That's what we really studied, and that's okay. We have to talk about CP2 minus a ball, which, if you think about, is the same as CP2 connect sum a ball, right? So adding a tube and then having a ball is the same as deleting a ball topologically from a closed 4-manifold. And we show that if K bounds a null homologous disk in CP2 plus B4, then S is greater or equal than 0. And similarly, if it bounds it in CP2 bar minus B4, then it's less or equal than 0. So that's some property of S with respect to surfaces in other 4-manifolds, not just B4. And then what does this have to do with Gluck twists? Well, one known property of Gluck twists is that if you add a CP2 to a Gluck twist like Z, you make it standard. You just get B4 plus CP2. And similarly, if you add a CP2 bar. But therefore, if you have a knot that bounds a disk in Z, then just add a CP2 to your Z, and you get that it bounds a disk in CP2 plus B4. And therefore, you get S greater or equal than 0, but then you get the same thing for CP2 bar, so S less or equal than 0, so S equals 0. So it's the same thing as in B4. So that strategy is not going to work for Gluck twists. We need some other construction. Okay, so now for some more, for a little bit of optimism and more positive result, it's work with Marengon and Piquirillo. So what we show is that some analog of the strategy works in other 4-manifolds. So we show that there exist homeomorphic 4-manifolds and a knot that bounds a null homologous disk in one of them minus B4, but not in the other one minus B4. So that implies that, so in other words, the set of such knots detects the exotic smooth structure for this kind of 4-manifolds. So we have, so one example is you take X to be this connected sum of CP2 and CP2 bars, and X prime to be K3 plus CP2 bar, and K be the trefoil. So it was known before that X and X prime are not diffeomorphic, but what the theorem says is that this exotic smooth structure is detected by the existence of a knot like this that bounds a null homologous disk in one and not the other. So maybe it's not hopeless to attempt this kind of strategy even for the for S4. I should mention the proof of this just uses gauge theory, not Khovanov homology. It uses the Seiberg-Witten equations. All right, so the third result is about a different construction of homotopy force spheres. So what we've decided is that Gluck twists are no good. I mean, they may give homotopy force spheres, but we don't know how to use the S invariant to detect that. So what's some other construction of homotopy force spheres? This is based on homeomorphisms between zero surgeries. So recall zero surgeries are these three manifolds that you build by from S3 by surgery along the knot. You take out the neighborhood of the knot and you put it back in. So now let's assume you have two knots such that the zero surgeries are homeomorphic. Or by the way, homeomorphic in dimension 3 is the same as diffeomorphic. In dimension 3, there's no difference between topological and smooth. Now suppose that one of them is slice, so it bounds a disk in B4. Then let's take the complement of a neighborhood of that disk. And it turns out that that has boundary the zero surgery. But we also know another manifold with boundary the zero surgery, namely the trace. So let's take the trace of the other knot of K prime. So again, we're looking at if one of them is slice, we look at the complement of the disk and then union the trace on the other knot. So they both have boundary S30 of K, which is homeomorphic to S30 of K prime. So we can glue them together and make a closed four manifold. Well, with some easy topology, you can show that that's a homotopy force sphere. It's homotopy equivalent and therefore homeomorphic to S4. So maybe it could be an example of exotic force spheres. We don't know. So this gives us some homotopy force spheres, and it turns out also that K prime bounds a disk in W. So it automatically gives us an example of a knot that bounds a disk in a homotopy 4 ball. So what we'd like, if we found some examples such that K prime is not sliced, right? That's the strategy. If S was non-zero for K prime, and we had this construction, then we would manage to disprove the smooth Poincare conjecture in dimension 4. We would get an exotic homotopy force sphere. Right, because K prime bounds a disk in this homotopy 4 ball, but not in B4. Now, one caveat about this is that we don't want phi to extend to a diffeomorphism between the traces, right? So recall from a disk, I had this 3 manifold, the zero surgery, and I also had the 4 manifold, the trace. And if I had a diffeomorphism of the traces, then it's not hard to prove that actually W that I constructed here is S4. It's standard, so it won't give anything exotic. So we want knots that have the same surgery, but different traces. And so these are not the kind of knots that were used, for example, in Piccirillo's proof that the Conway's knot is not slice. So there she needed knots with the same traces. Now we want knots with the same surgery, zero surgeries, but different traces. Okay, so how can we construct knots with the same zero surgeries? There are various constructions in the literature, like dualizable patterns, annulus twisting, and some satellites. They're a little bit ad hoc, and in some cases, they produce knots with the same traces. So instead, we made our own construction, so some work in progress with Piccirillo. We give a general construction of zero surgery homeomorphism between knots, which is based on some 3-component links called RBG links. I won't tell you what they are in general, but I will describe a special case that's of interest. So here's what a special RBG link. Let me just show you a picture. So it's a 3-component link made of three knots, a red one, a blue one, and a green one, such that if you forget about the green knot, then R union B is basically R union a meridian of R. So the blue knot can just act, is like, you can think of it as a small ring going around the red knot. And the same is true for the green knot. So if in this picture you remove the blue knot, then you can undo these twists and you just get, you see that the green one is a meridian for the red one. And then you need a little bit of a technical condition about the linking number between B and G. Let me not get into that. It has something to do, the red knot has to have a framing, which is some integer R. So that's a special RBG link. So from a special RBG link, you can obtain a knot KG by sliding G over R. Here's a picture of a slide. You just do it like this, and then you introduce some twists between them, which depends on this number R, the framing of the red. And similarly, you can slide B over R. And what you want is to remove the linking between B and G. I think I should just give you an example, but let me first state the theorem that if we have such a special RBG link, or we have a more general class of links called RBG, then you get a homeomorphism between the zero surgeries on the two knots, KB and KG. So here's an example. We have an RBG link on the left. The green knot is obtained by sliding the green over the red, and then you remove the red and the blue. And the blue one is obtained by sliding blue over red. So you get two knots with the same zero surgery. So what we want is to find some example where one of the knots is slice and the other one, so either KB or KG, the other one has S different from 0. If we could find this, then our W would be exotic and we would disprove the smooth Poincare conjecture. Because KG would be not slice, but it would bound something in a homotopy 4-ball. So the good things about these special RBG links is that you can draw many, many of them. So we studied 3,000 of them that come in a 6-parameter family. Okay, we didn't find any examples like this. We weren't that lucky, but still we found something. We found, for example, examples where one of the knots is sliced. There are plenty of such examples. And then the companion, the other one, we would like S to be non-zero, but typically S is 0. And it's either slice or we don't know if it's slice. Yes, so in any case, you do get a homotopy 4-sphere out of this. And we don't know if it's exotic. So it could be, I mean, the strategy doesn't work because S is 0, so we cannot use S to show that it's not sliced. But we get some homotopy 4 spheres, and they're still interesting. Maybe one could think of a different way of proving that they are exotic. Okay, but another thing that we get, which I think is more interesting, we get some examples where one of the knots has S different from 0, and the other one we don't know if it's sliced. So ideally, we would want it to be sliced. And what we find in these examples is that it looks almost sliced in the sense that, well, we couldn't show that it's either sliced or not sliced. So let me tell you what these 21 knots are. So first of all, let me state the theorem. So we found 21 knots. And if we could prove that any of them were sliced, then by what I said before, so we would have that S is non-zero for the companion, and then we would know that we would have an exotic 4-dimensional sphere. Okay, now the knots pass all computable obstructions to sliceness. So there are many obstructions to sliceness in the literature on knots. There are things coming from algebra, from the Seifert matrix, and there's the concept of algebraically sliced, one that passes all these obstructions, and all of our knots are algebraically sliced. They have S equals 0, so the Rasmussen invariant doesn't obstruct them from being sliced. And furthermore, for at least 5 of them, we can show that they are topologically sliced. So they satisfy this weaker condition that that they bounded a topological disk in B4. Okay, so here are some examples. These are the first 3 knots. So okay, there's some others, and there are some others, and here are some others. We find 21 such examples among our list of 3,000. The simplest one is K17. So K17 has 16 crossings, and it passes all these obstructions to sliceness. And we try to show that it's sliced. I mean, there are techniques for finding a disk. So this is a topological problem to find a disk in 4 dimensions whose boundary is this knot. You can try to find bands for it, but we couldn't. I mean, maybe it's not sliced. Maybe none of these are sliced. But at least what we have is that, you know, instead of something 4-dimensional, if you are a knot theorist, or if you like something more elementary like knots, it suffices to find a slice disk for them. All right, so these are the 3 results that I wanted to mention about this this strategy. And yes, I think that's all I had to say. Thank you.
Thank you.
Right. So now you can ask questions in Q&A if you'd like.
Thank you, Ciprian, for the beautiful lecture. Now it's time for questions. Any questions? You can post the questions in the Q&A box. So maybe I have the first questions.
Yes.
First of all, the terminology RBG just stands for the colors, right? Or does it have any?
Yeah, but it's also a pun, you know, on a Supreme Court justice that recently passed away.
Yeah. Okay. Okay, so you have these. Your statement is that about the I mean, if so, you say that you have this construction gives you all possible pairs of knots whose 0 surgeries are the same, right?
That's right. It's not the one I said, so it's more general than what I said. I mean, yeah, it's not. These are special RBG links, so there is a more general concept that I didn't talk about, which are called RBG links, and that gives everything. Yes.
But can you somehow reverse engineer the process in the sense that if I give you 2 knots, can you use this technology to determine whether the 0 surgeries are the same?
No. So that's a good question. So we don't know if you are given a knot. We don't know if it comes from this construction. We're trying to figure out what kind of knots come from this construction. But and we have some results. So but yeah, but in general, I don't know how to get the link from the knot. And in many cases, even if I do, so there are sometimes you just get you get the same knot back on the other side. So in some cases we can maybe make a link, but there's no guarantee that the blue knot won't be the same as the green knot. And in many cases it is the same.
Okay, so there's one question here. Yeah, I think you can read the question. Yeah.
Okay, how do you obstruct RBG links from having diffeomorphic traces? Oh, that's a very good question. Yes. You can abstract it even from having homeomorphic traces by some parity considerations. So if, yeah, so the, let me see, how does it go? By some, okay, so if two nuts have, I mean, okay, so there are two questions. First of all, if you have a given homeomorphism, when does it extend to the four-manifold? And that you can abstract using some condition on the intersection forms of the four-manifold, some parity condition. But then you can ask, what if there's some other homeomorphism that extends and you get a homeomorphism of the traces? And that, well, you can in many cases, you can just look at the self-homeomorphism group of the zero surgery. This is typically a hyperbolic three-manifold, and typically it's like its isometry group is just trivial. So there's a unique homeomorphism, and then you can use this intersection form obstruction to show that it doesn't extend to the traces. And then there are also some other obstructions like new invariants from Hegardt-Floer homology that can say something about not extending to diffeomorphisms rather than homeomorphisms.
Any more questions?
Okay, one more question.
Yeah.
If the zero surgeries on K and K prime are diffeomorphic, are there some general statements we can make about K and K prime? Yes, that's a good question. There's many things we can say. In particular, the Alexander polynomials are the same, and the signatures are the same. So many knot invariants are the same. Yeah, but the S invariant doesn't have to be the same. There are definitely examples that, I mean, like the Conway knot and its companion, such that K and K prime have different invariants, but some invariants are the same. Oh yeah, so the other question was, if for the special RBG links and the 21 knots in the result, have you checked that the diffeomorphisms don't extend? Yes, very good question. So the obstructions we have apply to roughly half of them. I forget how many exactly. And so for those, like, they don't extend to homeomorphisms. And for the others, we don't know.
Ciprian, again, for the, well, actually, I would say that on behalf of the audience, I would like to thank you for the wonderful, interesting lecture. And to the audience, thank you for your participation. I hope you enjoyed the rest of the joint meeting. Goodbye.
Goodbye. Thank you, everybody, for coming.